Thank you for your patience and thank you for coming. Hello, good afternoon. I am Albert Einstein. I'm here to tell you about my life and the contributions I made, many contributions to science. I revolutionized ideas about space, time, gravity, and light to all have a better understanding of our world and our universe. So, welcome to theoretical physics. A little bit lighter. Thank you. Thank you. Just a bit. Thanks. I was born March 14, 1879 in Ulm, Germany, and I would live most of my early life in southern Germany and Switzerland. My father was Hermann Einstein, a featherbed salesman, and then he got an electrical supply business along with his brother Jacob. My mother was Pauline Koch. And here I am as a baby, and here I am as a toddler. Everybody can recognize that. And I didn't speak till age 3, as some would consider me speech handicapped or intellectually handicapped, because it really took me to age 12 to fully understand word syntax, language skills, and sentence structure. See, I think in pictures, not words. And at age 5, my father gave me a compass, and I became fascinated by invisible forces and would do so for the rest of my life. At age 6, I started playing the violin and would do so also for the rest of my life. Early in life, my father lost his business in the Munich area in Germany because they wanted to make a bid on electrical supplies for the city of Munich, but using direct current. But that bid fell through because direct current is not practical. Alternating is. So he lost the bid, and then my family moved to Milan, Italy. But I stayed in Munich and went to school at the Lloyd Gymnasium in Munich. Here's the front of the school. Here's one of my classrooms. And here I am right here. By age 12, I self-taught myself geometry and Euclidean geometry and algebra. And by age 14, I self-taught myself calculus, outpacing the tutor my parents had for me. At this point in life, I liked playing the violin and reading books, philosophy books by Immanuel Kant. At age 16, I moved to Switzerland to continue high school around the Zurich area here, and became quite proficient and had a keen interest in math and physics, getting top scores in school. And also at age 17, then I renounced my German citizenship to avoid the conscription into the German military. And at this age, I would daydream what it would be like if I raced alongside a beam of light. If a light was like a wave, it would appear stationary or frozen. These are many thought experiments I would have in life, and they would greatly influence my work in the future. And at age 17, in 1896, I decided to enroll in a special school. It was for math and physics teaching school and a diploma school called the Swiss Federal Polytechnic School in Zurich. And I had trouble in the beginning because I couldn't pass the entrance exams to get in. I couldn't pass in language, history, and geography. Of course, math and science I did, so I had to go to trade school for a bit. When I came back, I had these professors to deal with there, and those are people who taught me. And at this school, I met a young Serbian woman named Milena Merrick, who would become my future first wife. And she was one of the few women in the school, one of the only women in my physics class, and we would take long walks in the Alps together and discuss science, as she was very good and excellent at doing physics. An excellent, capable student. And at this school, at the Zurich School, I studied James Maxwell's equations, which detail the nature of light, and realized that the speed of light remains constant in a vacuum. That is, it has a speed limit. This, however, violated Newton's theories of laws of motion, and that there's no absolute velocity in Newton's theories, and I knew one day I would have to reconcile the differences. However, at school, I rebelled against the rigidity of the constant learning by rote. Anything of creativity or originality was stifled. I was disinterested in school, was bored, cut classes. My teachers then told me I wouldn't amount to much, and therefore would not recommend me for a teaching job. So, I was able to graduate with a diploma from them in 1900 and became a Swiss citizen in 1901, but with no teaching prospects in sight. Whoops. At this point in time, around the turn of the century, my father, really a good man, was going bankrupt. Really a poor businessman, and he had a heart attack in 1902 and died at age 55. I was 23 then, and also had trouble marrying Mileva as it was due to some family pressure. So, a friend of mine recommended me for a job at the Swiss Patent Office in Bern, Switzerland, and there I became employed as a third-level, grade 3, low-level Swiss patent clerk. And here I am working there, by the way. And ideas crossed my desk, formal proposals from applicants, mainly about the synchronization of time along with transmission of electrical signals, kind of like a stoplight. But this job gave me the leisure then to work on my doctorate and also be surrounded by new ideas about machines, forces, and applied sciences. That is, how technology can influence and work with practical everyday things. And I know what you're thinking about in Switzerland. All we do is make chocolate bars, produce Swiss Army knives, produce cheese, and talk about mountains and cows, about nutty nutcrackers, and crazy cuckoo clocks. Well, maybe. In 1902, Mileva and I had a illegitimate daughter named Lysol, and we gave her up for adoption, and frankly, she was lost to history. In 1903, Mileva and I got married, and in 1904, we had our first child, Hans, and in 1910, we had another boy, Edward. My parents never really approved of Mileva, as she was an Eastern Orthodox Christian, and she was 4 years older than me. So we had some problems with that. And at this point, I would still daydream, what it'd be like to ride on a beam of light, but I wondered what happens if an observer were to watch me. Would the observer see what I see? Would I see what the observer would see? We'll have to see about the point of view. And in 1905, when I was 26, I produced my doctorate, which considered 4 papers that were published in a prestigious scientific journal. And this would be so influential that they would influence the trajectory of modern-day physics. I call 1905 my miracle year. And one of these papers described Brownian motion, which details how invisible particles, such as are in water or in gas, undergo rapid, irregular motion. I surmise that these particles, suspended in liquid or gas, are made of atoms, and when they collide, they are sent in a forward motion. I provided evidence and indirect proof that atoms and molecules exist through Brownian motion, and was able to calculate the size of these atoms. Secondly, another paper asserted that light is a wave, and that it interacts with matter, and that these particles of energy then come in minute, small bundles of energy, or quanta, or like photons, like bullets from a gun. And that light is composed of particles that travel as waves. Thirdly, I explored the photoelectric effect, or that a material will will hit something and bounce off with light. Fourthly, another paper described the equation E = mc² plus special relativity, where the energy of a body E is equal to the mass m of that body times the speed of light c, or 186,282 miles per second. This became the world's most famous equation and suggested that small amounts of mass are equivalent to large amounts of energy. Matter and energy were different sides of the same thing. It also explained the energy source of our sun, and this idea and equation will later be used to develop nuclear power, nuclear medicine, and nuclear bombs. You see, matter can be turned into energy, and energy can be turned into matter. And using the equation, if you accelerate matter m to the speed of light c, time very much slows down, your mass is very heavy, and your length becomes very much shorter. Let's follow up on that. Now, a mass m going the speed of light c equals the amount of energy needed to reach that speed. The amount of mass one would need to reach the speed of light determines the amount of energy to do that. E equals m means that energy and mass can be converted into each other. In everything, there isn't enough energy to reach the speed of light unless one adds more energy. But when one does that, one will have more mass to move. It will be an endless, vicious cycle. One can never achieve the speed of light as the object becomes infinitely too heavy after putting enormous amounts of energy to accelerate it to try to get it to light speed. Light moves at the speed because it has no mass. So when you accelerate to light speed, it becomes infinitely heavy. Everyday objects at rest with a modest amount of mass have a very large amount of energy inside of it, or some intrinsic energy or rest mass. When in motion, the body's total energy is greater than its rest energy plus its total mass. Now, I improvise all these theories not in the lab or with fancy equipment, but rather with thought experiments in my head. I was endlessly working out these ideas in my mind, and which would then cause me to be absent-minded at times and not pay attention to my wife and children. This led to the stereotype of the absent-minded professor. Now, with special relativity, not general relativity, became 11 years later, includes only the special case where motion is uniform or traveling in a straight line at a constant speed. As soon as one accelerates or curves, special relativity ceases to apply, and this is why they call it special. As soon as one accelerates, this theory concerns how to interpret motion between places that are moving at different speeds relative to each other. This special relativity created a fundamental link between space and time. The universe has three directional vectors, or really three dimensions, and that is up, down, left, right, and forwards and backwards. And then there is the fourth dimension, which is time, or the space-time continuum. If one travels fast enough through space, the observations one makes about space and time differ somewhat from the observations of other people who are moving at different speeds. And in this thought experiment, we'll start with this one up here. If you or another astronaut are moving in different spaceships and want to compare your observations, all that matters is how fast you and the other astronaut are moving with respect to each other. So, in the top figure, if you're in a spaceship traveling at a constant speed, half light speed, then holding a laser, so it shoots a beam of light to a mirror on the ceiling, and then it strikes the detector on the floor, there's really not that much difference at all. Typical right angles and what we'd expect. However, a slower astronaut, shown here, spying on you and watching this same experiment, would see things differently. He would see the beam of light strike the mirror, but travel in a diagonal path to the mirror, and then strike downwards to the detector on a diagonal path. So both you and the astronaut would see, the slower astronaut, would see different things for the beam of light trajectory. They are not the same length. This means the time must be different for both in the experiment. Same thing here. The typical right angles we saw, but an observer on Earth would see the beam of light travel in a diagonal upward and then downward. Now, with this thought experiment, this is the elevator thought experiment. The elevator is really could be a laboratory. If you drop a ball in an elevator that rests on Earth, of course it will fall to the ground at 32 feet per second, 10 meters per second. However, if you are in a spaceship way out in space and drop the ball but are accelerated at 100,000 miles per second and drop that ball downward, and this is going, and you're going forcing upward, the acceleration, the ball will also drop at 10 meters per second. And the next slide concerns the principle of equivalence. If you are in an elevator falling freely toward the ground, you would feel a bit weightless, and so would the ball you would drop. And it would be the same feeling that you would have on a faraway star or another planet, the principle of equivalence. These ideas I thought of in 1905 became the underlying general principles for the general relativity in 1916. With special relativity, no matter what speed an observer who is racing next to a beam of light must always observe the same velocity of light, or light speed. Laws of physics are the same for all non-accelerating observers, and that the speed of light is independent of the motion of observers. To make the speed of light constant, space and time change in a moving body as seen by an outside observer. And one, that the body or mass at super-fast speeds becomes shorter or contracts, and two, at these speeds, time moves slower and dilates, and then three, mass increases with speed. With time, you can only go forwards, not backwards. Why? Because our universe unfolded outward and forward 13.8 billion years ago, and this is why time acts in this progressive manner. And as Beloved told me, you cannot unring a bell. Rising rapidly in the academic world, I was invited to speak, well, let me go back a bit. In 1908, I became a lecturer at the University of Berlin and returned to Germany and became a German citizen and was appointed to be with the Prussian Academy of Sciences, shown here. This later turned into the Kaiser Wilhelm Institute for Physics in Berlin. That is, I would stay in Berlin to the 1930s, and of course I lived and worked there. However, rising rapidly in the academic world, I was invited to speak at many international conferences in Europe and abroad, and was on the road a lot. An emotional chasm developed with Beloved. I would write her letters, here I am writing by the way, or she and I would argue about our children and finances, not to mention my preoccupation with relativity. My marriage was not a happy one. I then began an affair in 1912 with my cousin Elsa Lowenthal, and divorced Beloved in 1919. 4 months later, in June of 1919, Elsa and I were married. Elsa already had 2 daughters from a previous marriage, and she had proved to be very supportive of my ideas and lecturing. Very easy to work with. Now, going back to 1905, I began working gravity into my theories because special relativity, the special one, only concerned constant motion without gravity or acceleration in mind. But it did set the groundwork for general relativity 11 years later. This did not explain the universe enough with special relativity. My paper in general relativity was put forth in 1916, and it truly shook the world because it comes from a point of view, or how an observer and a participant each view things. And that one could take a subject and express it from other points of view is the key thing here. Since art imitates life, my ideas became a turning point or a new reference point in many artistic mediums. So I'm going to digress for about 2 minutes and talk about art and see how this really relates to this. The Cumulus Movement began in Paris in 1907. The Cubists broke from centuries of tradition by rejecting the single viewpoint, and instead, three-dimensional objects were fragmented and redefined from several points of view simultaneously, just like my theories. Works by Braque, Picasso, and Duchamp broke up a world and reimagined it, much like I did at this point in history. This fragmented viewpoint also became apparent in sculptures, as you can see, taking things from different angles and looking at it. and also in interpretive dance like Igor Stravinsky's The Rite of Spring in 1913. The choreography and music was so non-traditional and personal, it caused riots when performed in Paris. Also, photography as a modern art form came into focus at this time, with Alfred Stieglitz here and his photo succession group. This liberated photography from conventional photos to more realistic scenes, artistic modernism, and personalized subjects. That is, from personal points of view. This would be one of the greatest photographs ever made. And in 1906, Upton Sinclair, a muckraking journalist, wrote The Jungle, which described horrible, unsanitary conditions in the meatpacking business. This led to the Pure Food and Drug Act in 1906, passed by Teddy Roosevelt and his administration. And this book personalized the plight of immigrant working-class people and is a reaction to industrialization. Other books at this time exposed child laborers, like Spargo's The Bitter Cry of Children, and Lincoln Steffen's The Shame of Cities, which detailed urban corruption from a personal standpoint. At this time, Frank Lloyd Wright was designing his prairie houses and radically transformed our thinking of interior space. His ideas revolutionized our ideas about the personal connection we have with our homes to our environment. Thus, my ideas about how one interprets time and movement were in sync with other art forms at the time. We had to jump out of ourselves and look at things from different perspectives to get a better reality, which is what my theories are really all about. Now, concerning general relativity, getting back to physics, I rewrote the laws of gravitation that have remained unchallenged since Newton in 1687. Now, before I get into this, I really got to complain about Newton's hair. Honest to goodness, look at all that stuff. He looks like a pair of poodle in heat. Every time we have a discussion of him, his hair always gets in the way. One would think that this club, whenever they talk about Newton, would say something about his hair. After all, that was really kind of important. His spirit and I actually met up later on, and we talked about things, and he insulted me by calling me Herr Professor. This is a German thing, not lost. But anyways, I still love him, but I don't like his hair. Anyways, Newton described gravity as a force that pulls objects of mass together, but kept gravity separate from acceleration. Before I came along, mass and energy were viewed as completely separate. With Newtonian physics, space was a vast, static, fixed container of primordial ether with large bodies that moved through it, embedded with two-dimensional Euclidean geometry. Newton's model of gravitation was a force of attraction between two masses. Rather, I conceived of a vast and grand gravitational field being space itself. Space and gravitational fields became the same thing. So our Earth does not orbit the sun by some mysterious force. Rather, it is racing in a space that inclines like a marble that rolls in a funnel. And the curved nature of the walls itself cause the marble or Earth to roll, and that's Einsteinian geometry and physics. So, it would be like this, and that's why the Earth travels in this kind of ellipse around the sun, and in that kind of trajectory. According to my general theory of relativity, 1916, stationary clocks that are farther away from Earth tick a bit faster than those on Earth. Earthbound clocks are slowed by Earth's gravity. Clocks higher up run a bit faster than clocks down below, and I mean billionths of a second. Earthbound clocks are slowed by Earth's gravity, while clocks in orbit or stationary in space run a bit faster since there's less gravity to slow time. We know this is true because atomic clocks, much later, after I died, were put on high-flying planes where the pull of gravity from Earth is weaker to test this theory. These clocks ran just a bit faster than Earthbound clocks. In 1976, clocks were put on planes miles up, and these clocks ran 1 second faster for every 70 years. This situation also happens with today's GPS satellites. The clocks on these satellites run a bit faster than Earthbound clocks and need to be calibrated daily for us to have pinpoint measurements when we travel. Otherwise, we'll be 6 miles off on every trip we calculate, and we'll all end up in Fenny. Events that occur for one observer can occur at different times for another. That is, anything heavy in space, like for instance our Earth, would leave a depression in the space-time fabric. And this now, it does a couple things. It slows time down as you get more toward the center of the large mass of gravity, and that light can be distorted from it or bend or curve, which we'll get into. This all leads to the twin paradox. This is a thought experiment where there are twins Joe in the spacesuit and Mo, his brother. Obviously, they're twins. On their 20th birthday, Joe gets in a spaceship and travels near the speed of light for 5 years. So here's Joe traveling, and here's Mo left stuck on Earth. So actually, the trip is for 5 years, and so when Joe returns to Earth, he is 25 years old, where Mo remains on Earth, and when Joe gets back, Mo is 95 years old. So here's Joe on a spaceship, travels away, leaves Mo here, and Joe gets back, Mo was 95 years old. So how could this be? Since Joe was moving so rapidly, time became slower for him. Atoms in a very fast vehicle move slower than stationary ones do. The faster someone goes, the more time is affected. Time is not a universal measurement. Rather, it depends on speed and acceleration at the moment. Moving clocks run slower than stationary clocks do, and the slowing down the clocks due to high speed is called time dilation. Since planets and stars bend the fabric of space and time like bowling balls on a trampoline, the closer you get to these objects, the slower time moves. Now, my general theory of relativity predicted that my general theory in 1916 predicted the existence of black holes. Stephen Hawking in the 1970s would further elucidate it. Light cannot escape from a black hole because a super heavy iron core left over from a large giant sun, which becomes a black hole or singularity, wraps space around it and prevents anything from light from escaping from it. Now that's some pedantic stuff that you would get in an encyclopedia. How this works is this. I need about 90 seconds of your time. This is our sun, and clearly, I think I have the wrong slide up. This is our sun. Thank you. This is our sun here. Now our sun weights down the fabric of space because you can put 1,300,000 Earths inside of our sun. So, and it creates a depression in space. So, 4 billion years from now, our sun's outer shell will disintegrate, and what's left will be a heavy iron core we call a white dwarf that won't give up much light or heat, but will weight down space, and be called a white dwarf. A star a little larger than our sun, with a diameter of about 1 million miles or more, will become, the outer shell will blow off into a supernova, and what's left will be a super heavy iron core called a neutron star. Now, a fistful of this neutron star will weigh 30 billion tons, as much as 30 Mount Everest, and will really, really weight down the fabric of space because it's so super heavy. However, a larger sun, maybe about the size of a beach ball, compared to this model here, one that's 2.5 times bigger than our sun. The outer shell will blow off, and what's left will be a core, and be a very heavy iron core, but it will implode and become a singularity, a place or a point of infinite density, and really weight down space, so much so that space and gravity overwhelm it, almost like a blanket on top of it. And you can think of this as like, you can think of this as like this whole room being a giant trampoline, and then, which is space, and if you put an elephant on top of it, what's going to happen, which is the heavy material, the trampoline or the space will overwhelm the elephant and circle over it. So this is why this happens. It'll have a singularity here, an event horizon, where no light can escape, and an accretion disk on top. That's what they call a black hole. And no, I didn't have these theories, but I got them from Stephen Hawking. Whenever no, you gotta stay. Stephen Hawking here, our spirits met and talked about this. But this, I did not predict this, but I predicted black holes. Now, these black holes can have a galactic one in the center of all galaxies, billions of miles in diameter, or a smaller solar mass about 10 times the size of our sun, being the size of Rhode Island, and will have a large accretion disk on it. Now, so how this pertains is, for instance, an astronaut watching a clock fall into a black hole would see its hands slowly and gradually slow down as the pull of gravity increases. The second hand would move or tick once every hour, then once every decade, and finally would appear to be stuck or frozen and very elongated, and would disappear at any time in this scenario. So time moves slower near very heavy, massive objects like the singularity I told you about. Same thing would happen if you watch an astronaut fall into a black hole. The astronaut will tumble slower and slower as she approaches it, turning redder and redder, that is redshifted, or very much accelerated, and appear to be stationary or frozen, and then maybe disappear. Of course, there's an image we see as an outside observer of the astronaut. But in reality, the closer the astronaut gets to the black hole of singularity, the further that astronaut gets lengthened out as to be thinner than a human hair or spaghettiified. And once at the event horizon of the black hole, since matter cannot be lost or gained, the astronaut in her spacesuit will become a hologram. The information on how the atoms and quarks of the astronaut and her spacesuit are arranged and configured will be saved in a holographic projection just above the event horizon. Thus, time slows near very heavy objects, and the matter then falls into the gravity of a black hole, as shown by these examples here, can be converted into energy with nothing lost or gained, maintaining a balance in our universe, a yin-yang. Whatever speed we move at, light travels at 300 meters per second in a vacuum. Their time passes more slowly for people traveling at very high speeds compared to people traveling more slowly, and that energy equal mass times the speed of light squared, or E equal mc squared, and that energy and matter can be converted into one another. I showed that matter causes space to curve, therefore making gravity. And gravity is acceleration, and I realized this by age 30 in 1909. Light follows a path mapped out by a gravitational curve of space. So when light comes near something that's very heavy, it's deflected and curves a bit. Now, with the general theory that I had in 1916, it also predicts that when light travels through the fabric of space, that it can be warped, bent, or twisted due to massive objects. That means the light from a star coming by the sun would be bent before it comes to Earth that we see it. Stars are very heavy, massive objects that create a curve in space. The warping of space-time causes light to be deflected, and gravity then is a manifestation of the curvature of space. That means that the stars are here. This is how they really are. But if there's our sun in between them, then what happens is they're perceived to be further away, or here to be further away, but rather they really are here. Let's go into this. Now, this radical idea I had was tested during a total eclipse of the sun in May of 1919. Then the position of some nearby stars were carefully measured during the 6-minute eclipse and were compared to their normal positions in the sky, with the eclipsed sun directly in between them. So the light from the star then follows this trajectory. Indeed, a ray of light from a nearby star, nicking the edge of the sun, was bent 1.75 arc seconds, or 1 inch or 2 miles long. This confirmed my general theory that space is a 4-dimensional continuum called space-time. so that gravity does bend light. And we had a lecture here 2 weeks ago about Hubble. When Hubble does this, it has to make up for the difference by where the observed one is and where the real star is because of the curvature of space, because of the deflection caused by a heavy, massive object. My general theory of relativity predicted gravitational lensing, which is a manifestation of space being warped by massive, heavy objects, like neutron stars, magnetars, white dwarfs, and particularly black holes. This type of lensing magnifies stars and galaxies we see in telescopes and makes them look closer than what they really are. The light from objects that lies beyond these objects literally appears in a different location in the sky. Besides predicting these gravitational lensing, I also predicted gravitational waves. That is, waves of energy sent as ripples through the space-time continuum. And how does this happen? Well, maybe two neutron stars got too close together or bumped into each other and caused these massive waves to be sent through our universe like this and cause ripples in the space-time. This also could have been from two black holes that got too close together and sending out these huge shock waves that went through our system, our universe, excuse me. And this was actually proven in 2016, 5 years back, when two black holes collided and sent gravitational waves, and they were able to be detected by the Laser Interferometer Gravitational Wave Observatory. And that is, it picked up a little blip on the screen. And this helped prove my theory that I predicted, the general theory, that this could be detected even though the event took place 1 billion years ago. That is, two black holes bumped into each other, sent these shock waves 1 billion years through our galaxy, and we're still feeling the vibrations from it if you measure it very carefully. And you're right, I don't really have any cracks in my theory. So how does this relate to us? When two black holes collide, they produce tsunami-like waves that sent through a galaxy, and this helped kickstart the start of our solar system. First, it started spinning 4.5 billion years ago. That is, the waves from these kind of black holes, gravitational waves, came in the area where our nascent solar system was being formed and helped kickstart it by swirling. And that's why the Earth revolves around the Sun at 67,000 miles per hour, over 1,000 miles per minute. So, therefore, massive objects cause a distortion in space-time called gravity. Space and time were interwoven into a single continuum known as space-time. A massive object would press down into the fabric of space and cause a dimple. Also, gravity is not a force, but a distortion of time and space. Gravity and acceleration are the same. Gravity is a curvature of time and space caused by mass and energy. In essence, in the early 20th century, I helped create a new exciting field called cosmology. Cosmo what? Well, we could have Cosmo magazine, cosmetology, Cosmos restaurants, and I swear every Italian race car driver's first name is a male is Cosmo. Okay, so, of course, we still use standard Euclidean 2D geometry to really travel in space. At 9 miles per second, you have to, but at 100,000 miles per second, things change. That is, my universe is hyperbolic, that means it's saddle shaped, and that is, light bends and curves due to distortion of gravity. And it's also could be also parabolic, or could be like a Mobius strip, if you want to think of the universe in terms of what it looks like. So I received the Nobel Prize in Physics in 1921 for the contributions to theoretical physics and for my discovery of the photoelectric effect. I also went on world tours at this time, speaking in the US, Japan, France, and England. I spoke to audiences about relativity and cosmology, or the nature and structure of the universe. My equations predicted a universe that was not static, but dynamic and expanding or contracting. To stabilize my predictions, I developed a cosmological constant to make the universe a steady state one that was neither expanding or contracting. And this later on proved to be my greatest blunder. You see, Hubble had proved in 1930 that the universe to be expanding with empirical evidence of receding or redshifted galaxies. That means whenever we look at galaxies, they are slowly ebbing away from us. And the light from these galaxies has a spectrum toward the red end of the spectrum, which means the light is going away from us. Much like the sunset or a sunrise, it's always orange, red, or purple because the sun's rays are at an angle to us and are being stretched out and away from us as the Earth turns. When I first came to America in 1920, I was treated as a celebrity because of the 1919 eclipse proof detailed to the public in newspapers of the curvature of space. I became the first celebrity scientist, and my name became synonymous with genius. I traveled to many big cities and was greeted by mayors, plus was honored at very large public ceremonial banquets. In the 1920s, I became a professor of physics in Berlin, giving lectures. However, by 1929 to 1930, a number of German scientists had called my work Jewish physics. And the growing Nazi movement there enlisted 100 scientists that were really pro-Nazi and Germans, publicly denouncing my work and writing. There was much antagonism about me, with death threats too. A reward was placed on my head, and a number of prominent Jewish men I was friends with were murdered. Around this time, my works and papers were burned, and a summer cottage I had in Berlin was turned into a Hitler youth camp. And this is, the big cheese is right here, and this is pretty bad if you ask me. So I left Germany and renounced my German citizenship in 1933 and traveled with Elsa to a rural England town and was guarded there by local people there with guns. And I became a national treasure. Here I am with Elsa, and they're guarding me right here. I immigrated to the U.S. in October 1933. Elsa and I had 30 pieces of luggage. And this was the third time I've been to the States, and this time I didn't leave. I took a position offered to me by the Princeton University in New Jersey at the Institute of Advanced Study and stayed there with Elsa the rest of my life. And here I am, by the way, in my living room there. We're at a house. I went to their graduation ceremonies at Princeton and was involved with the faculty and many people that came by. I was very much involved. And I became a U.S. citizen in 1940. Here I am taking the Pledge of Allegiance and was able to do my research at this place, study what I wanted, and give lectures. I had carte blanche to do my thing. For the last 30 years of my life, I worked on the unified field theory, which tried to combine the four main parts of the universe: electromagnetism, gravity, along with the strong and weak forces, into one elegant theory, or the theory of everything, or the grand unification theory, guts. And that is, you combine gravity, the weak, electromagnetic, and the strong into guts. I wanted to put it all together for a vast, encompassing idea of our universe in simple, elegant terms. Excuse me. However, quantum mechanics, or the behavior of building blocks of atoms, would confound me and even future physicists. You see, at the basic subatomic level, quarks, that is inside atoms, inside the nucleus, have the probability to be in one place and not the other. Quantum mechanics, or quantum physics, is so bizarre at this very subatomic level that I call it spooky action at a distance, or spooky connections. This actually concerns entanglement. That is, when a single photon of light breaks into two separate pieces and go in two different directions, and thus are separated even by billions and trillions of miles of space, and then observed by a third party, they can somehow communicate instantaneously with each other or be entangled. When one observes the spin of one of these photons, one will know the spin of its twin partner in an instant. Looking at one reveals the other, even light years and right away, light years apart and right away. A particle, therefore, is not real until it is observed. A light particle or a wave or cloud of probabilities exists until it is observed. And this sounds improbable and impossible, but this is what they're finding out. Further applied and further extended, an action in one place can have an instantaneous effect anywhere in the universe. You see, my theories concern general relativity applied to the big picture or the macro level, but conversely at the micro level or deep inside my atoms, my laws break down. That's why I could not get guts. Common sense and everyday laws are thrown out the window as chance, non-order, probability, and randomness reign supreme. That is a fuzzy wave of probabilities when the elements of light are observed. Although in my mind I would fight and be confounded by quantum mechanics and its fleeting randomness, other physicists would think differently. They say the universe is a casino where our fundamental laws are broken. Therefore, reality is an illusion where trillions of bits of information are projected on a universal cosmic wide screen that we call reality, or a vast encompassing holographic projection. Space and time are created by entangled particles, which is the true fabric of our universe. So it's projected as a hologram to us. And if you're wondering why this is so, or why this can be, this is why light acts both as a particle and a wave when passed through very narrow slits of barriers in a lab onto a back screen. The light is a wave when observed one time, or has wave-like patterns on the back end of the screen. And then a particle of dots another time on the same screen when the experiment is repeated over and over. That is, one time you look, it's a wave. Another time you look, it's a particle, no matter how many times they do the experiment. And yes, this is hard to follow, which concerns the Heisenberg principle. That is, when you start studying anything at all, like these subatomic particles, one alters and changes their movement. Therefore, I rejected quantum physics because, in my eyes, God does not play dice with the universe. And I rejected these. Therefore, I could not put guts together. And at this level, these particles have no measurable gravity. In the 1980s, string theory tried to bridge the quantum mechanics with my general theory of relativity. And that is, matter's here, and inside matter are molecules, inside molecules are atoms, inside that is a nucleus, and inside some of that are quarks, and inside that are strings. And the name string theory comes from the modeling of subatomic particles as tiny one-dimensional string-like entities. These strings then vibrate to correspond to a particle with definite properties of mass and charge. This then has a potential to combine the four main forces of the universe as mentioned. But I believe I've been looking for the Holy Grail, because now string theory is more or less a mathematical construct. Quantum physics is still not tied into general relativity. Sometimes great, grandiose, all-encompassing theories tied into elegant math-sized light equations say more about our needs than as a species than the universe itself. It tells more about us and our needs than actually what's going on. So, on a personal note, this is where I live in Princeton with Elsa. And Princeton's, by the way, on the middle part of the state toward the western end. And this is my office, typical physics professor's office with papers everywhere. Here I am being interviewed, and my papers here. And I like to smoke a pipe. I really had a problem with socks. I really didn't like wearing socks. Why should I? No one's going to make a judgment about me. And I didn't cut my hair. Why didn't I cut my hair? I wasn't there to impress anybody. My ideas were the most significant thing. And I often wear sweaters to work. pretty laid back about the whole thing. Reminiscing a bit, on one of my visits to America in the early 1930s, I met Charlie Chaplin, shown here. And the two of us immediately became friends. I came to see his premiere of his film, City Lights. Crowds of people mobbed us and clapped as I looked bewildered as Chaplin said to me, "They're cheering us both, you because nobody understands you, and me because everybody understands me." In 1939, I wrote 2 letters to President Roosevelt explaining the potential power of nuclear weapons and the distinct possibility that I had heard from European scientists of Nazi Germany developing such devastating weapons. I wrote him to try to convince him that the U.S. needs to win the race to build the bomb. This then culminated in 1942 with the Manhattan Project for the development, construction, and testing of the first nuclear weapons detonated in the New Mexico desert. I was never involved in this monumental, super-secret project. I later regretted urging on FDR and wrote another letter to him right here, this is FDR, trying to dissuade him from building the bomb and using it, since I was a pacifist. In July of 1945, the first bomb was successfully tested and used, and this ushered in the nuclear age. By then, everybody realized my famous equation, E = mc squared, or that energy and mass are related, helped push us into this age. In this new world I created, mass became a way to measure the total energy in an object without it being heated or moved. Mass is a super concentrated form of energy, and the splitting of the atom, or fission, using uranium, releases huge amounts of energy. This then resulted in the Nagasaki and Hiroshima bombings, ending World War II. On a personal note, I learned to play the violin. It soothed me and gave me peace, and music is really math, as we all know. I was a staunch pacifist all my life and believed the cause of the ills our world has was by excessive nationalism. Over-enthusiastic pride and arrogance about one's nationality can lead to violent, deadly confrontations, and we've all seen this in our lifetime. I do not believe in a God, personal God that intervened in humanity's work, but a God of harmony and beauty. I retired from Princeton in 1945, and then I joined the NAACP, and I made speeches for the nascent civil rights movement and spoke to black audience. Why would I do that for? Because I felt like them. In my own home country, I was discriminated against, had to leave, otherwise I'd be killed. And I came here to America, I was accepted at Princeton, but people did not trust Germans during the 1940s in America and the 1950s. And this is kind of sad, all because we were of a nationality. So, by 1955, J. Edgar Hoover had compiled 1,400 pages of documents against me. Here I am mentioned about a subject they were interested in. Imagine 1,400 pages about me, a simple physicist. In 1952, Israel's first president, Chaim Weizmann, asked me to become the president of Israel because he told me I was the greatest Jew alive. I was 73 years old then and turned him down because I told him I couldn't deal with objective matters. I couldn't deal with people. I do better in dealing with objective matters. He wanted to be president of Israel. Here we are together. Here we are together with some people. And really, there are dozens of science concepts, schools, streets, buildings, and awards named after me. There are over 40 scientific and math concepts named after me, along with 5 tech gadgets, 12 schools, 15 streets, 5 buildings, 10 multimedia awards, like TV shows, 5 prestigious awards, 15 various things, like the lunar crater, Einsteinium, streets, sculptures, stamps, observatories. If your name is mentioned with my name, you're in big company. In April of 1955, I suffered an abdominal aortic aneurysm after refusing surgery at the University Medical Center, and I died. I was 76 years old. Per my wishes, my brain was kept by the Princeton University Medical Center and used for the study of neuroscience. My eyeballs were given to my doctor. My papers were turned over to the Hebrew University in Jerusalem, and my body was cremated and my ashes scattered. Later on, my brain was kept in a jar and moved around to various places for years and photographed, and later sectioned into 240 very thin slices to be analyzed over time. It was found that my brain's parietal lobe, where math and reasoning occur, was larger than other people's. In conclusion, I led a wonderful life, and I was on the cutting edge of the journey that mankind would make in explaining our universe. Of course, it's going to take hundreds of years to prove all my theories correct, as empirical proof will be needed. Remember, fantastic claims require fantastic proof. Meanwhile, embrace cosmology. After all, everything is relative. And thank you very much. That is the end.